What's up, calculus students? We're going to do the third homework. Remember, the overarching theme of this unit is taking antiderivatives. We will be taking antiderivatives today. However, we're going to take a little side topic and talk about slope fields. Now, the key to lesson 3 and lesson 4 is we're going to attempt to take antiderivatives of x's and y's. We'll be doing that later in this homework. But what we started with in the lesson was this idea of what if you don't know how to take the antiderivative? Is there a way to possibly see what your antiderivative looks like, what the equation could be, without actually taking the antiderivative? And this is what a slope field's about. If you remember in class, we talked about, hey, do you remember back in the day where I gave you like an f and you were to sketch f prime? Well, we would use these like little tiny slopes and understand their value. And we understood there for like what f prime's values would be. The idea with the slope field is if you know what the slopes are going to be, these are the slopes, do you understand what the shape of your solution f is going to be? So these are f primes. This is what f would have to look like. Now the problem with slope fields is that you're not exactly sure where the graph passes through. The whole idea of the having a plus c, meaning you could be shifting things up or down, or lots of things could change, which is why we're not going to just see like one set of slopes in specific locations. Instead, we'll have like a large collection of slopes, which gives us all of our possibilities for what the original function looks like. So here would be like a slope field where like, oh, the solution could look like that. The solution could also look like that. And again, what's the difference between the two? It's just whatever the plus c ends up being. So that's the idea. Now, how do we do this? We're going to just assume we have these points. These are points on our antiderivative. Find out what the slope is. So what you have to do is, understand where the point's located, say 2, 1. Take that point, plug it into your dy dx, and you get a slope, 3. A dy dx at this point is 3. Now you just got to understand what a slope of 3 looks like. It's down 3 over 1. So I'm like aiming at that slope there, or at that point there, so that I have like the correct pitch of things. And then we keep going. I can do 2, 0 and get 2. Slope of 2. Wait, this is 1, 2, 3. I should be aiming down towards this bottom point here. This, I should be aiming down at this bottom point here as well. If I have the point to -1, the slope is 1. Aim down and over 1. Let's look at the point 1, 3. 4. Aim 1, 2, 3, 4. Aim all the way down there. 1, 1, the slope would be 2. Aim here. 1, 0, the slope would be 1. 1, -1. If I plug in 1 and -1 into, again, I'm plugging it into here, if that wasn't clear. The slope would be 0. 1, -2. Now I have my first slope of -1. And we're just going to keep going. 0, 1, the slope is 1. 0, 0, the slope is 0. I don't have the point there, but assume it's there. 0, -1, -1. Let's do this point, -1, 3. 2. -1, 1. Sorry, that's negative 1, 2. It's important to keep track of everything. If you need to list off the points, do it. If you want to do it on the side, do it. If you think you can do it by eyeballing it, do it. Just get it right. This slope is 1. This slope, negative 1, 1 will be 0. Negative 1, 0 is negative 1. Negative 1 is negative 2. Negative 1, negative 2 is negative 3. Negative 2, 1 is going to be negative 1. Negative 2, 0 is negative 2. Negative 2, negative 1 is negative 3. And you could see like the zero slopes. You could maybe see like this line would work. Like there's like shapes that fit here. And this is the idea of how a slope field can help you see what the antiderivative would look like. We're not going to take the antiderivative of this specific one because we don't know how to, but the ones we're going to see later, we will be able to. All right, x squared times y. Now, whenever you see like things that are multiplied or you see situations like this, any situation, it's easy to knock out the ones that are easily done. For example, when y is 0, dy dx has to be 0. When x is 0, dy dx has to be 0. So I can go ahead and just knock out these slopes when y is 0 and when x is 0. Cool? X squared y, 1, 1, 1. 2 squared is 4 times 1 is 4, so like pretty steep. 1, 2 will be a slope of 2. Sometimes you could stay on like a specific column, so stick with when x is 1. You're just going to worry about the y. So y negative 1, y negative 2. Same thing with x is negative 1. Negative 1 squared is 1. So I'm going to have the same slopes here as I do here because like 1 or negative 1 being squared just makes this 1. And so I have a slope of 2, 1, negative 1, negative 2. Really, we will see that kind of symmetry with the x's and the y's. If x is negative 2 squared is 4. So negative 2, 1 will be that positive 4 like I saw here. 2, negative 1 will be negative 4. We'll see that symmetry here, negative 4. And we did it. And again, you can kind of see maybe some shapes that fit, and that's the key to slope fields. Last one that we're creating. Excuse me. X squared minus y squared. Well, some easy ones. If x is equal to y, then the slope is going to be 0. So 1, 1, the slope is 0. Also, if x and y are opposites of each other, the slope are going to be 0 because you're just going to be subtracting the same number when you're opposites. So all the 1, 1s will have a slope of 0. All right. Any other easy ones? 0, 0, the slope is 0. Cool. Why don't we just focus on a specific row? This is another approach to do it. Like just say, okay, y is 0. What is x squared? Okay, so it's like x squared minus 0. This is going to be 4. This is going to be 1. This is going to be 1. This is going to be 4. Y, negative 2 squared is 4. Cool. When y is 1, I'm going to have my x value. And again, it's going to be symmetrical because of like the squaring of things. So like symmetrical here. So my x is 4 minus 1 is 3. 1, 2, 3. Aim at that one. Y is 1, x is 0. So that'd be minus 1 because it's 0 minus 1 squared. Negative 2, 1 will be 4 minus 1, which is that 4 right there. Let's do y is negative 1. Again, if y is negative 1, you're going to have the same things as here because negative 1 squared is 1. So you're going to have here 4 minus 1, which is 3. Same slope as this guy. Negative 1, 0, negative 1. 0 minus 1 is negative 1, so it's the same as that guy. So like it works out. Here, negative 2 squared is 4, minus what will be 1 after you take negative 1 square, so it's going to be 3, so it's the same slope as that guy. And let's do 1, 2. So when y is 2, I'm going to be subtracting 4. So 1 minus 4 is negative 3. 1, 2, 3, shoot for that guy. Same here. It'll be 1 minus 4, negative 3. Here, these will be the same as those. There's a lot of symmetry here. X is 1, so it'll be 1 minus y is negative 2. That's going to be 4. So 1 minus 4 is negative 3. Here, same deal. X is negative 1, so that becomes 1 minus 4 is negative 3. Okay, a lot of symmetry with these. You'll see symmetry with slopes. All right, cool. First thing you need to know, creating a slope field. Part of what you need to know is matching slope fields with its differential equation. It's kind of like the idea of creating. So I'm going to pause on drawing a potential solution until later. I'm instead going to be like, which one of these differential equations creates this slope field? Now, some things to notice. When x is 0, I have these horizontal tangents here. When x is 0, I have horizontal tangents here. So these two, when x is 0, dy dx equals 0. Okay, which one of these, when x is 0, is dy dx 0? That guy? And that guy, when x is 0, dy dx equals 0. So I know 2x is one of these, and I know x squared is one of these. Cool? Which one's which? Well, like if I plugged in a half, I'd have a slope of 1. Okay, if I plug in a half, this would be a slope that would be a fourth. If I plug in negative 1, I should see a slope that's negative here, whereas if I plug in negative 1, I see a slope that's positive. You notice all of these slopes are positive or 0. These slopes could be negatives or positives. That's how I know 2x must create that slope field. X squared must create this slope field. Cool? This is kind of how we work with things. What's the next one? The next one I notice, like, you don't really see it, but there are vertical tangents here. When x is 0, dy dx is undefined. Which one of these, when I plug in 0, do I get an undefined? Well, it's either this or this. This is 0 over 0, which means it's going to approach something. I'm going to pause on this one. I feel like this is one, but let's just kind of write down those two options. I don't like using red all the time. Let's see. We should know this jump function produces values that are either positive 1 or negative 1. If I plug in 2, I got 2 over 2, 1. If I plug in negative 2, I got 2 over negative 2, which is negative 1. You should kind of understand / see this idea that the slopes are all consistent on one side of things and all consistent on the other side of things. Now, I'd probably have this missing. I think this is shifted over a little bit. But absolute x over x versus here, if I plug in 0, undefined, that's good. If I plug in positive values, I have positive slopes. As I plug in bigger and bigger x values, the slopes will get less and less and less. 1/5, 1/6, 1/7. If I plug in negative 1, negative 2, negative 3, negative 4, negative 5, my dy dx's will be negative 1/3, negative 1/4, negative 1/5, negative 1/6. That kind of confirms that we have that. The last two should kind of make sense just by looking at it and thinking about antiderivatives, but watch. We either have cos x or e to the x. If I plug in 0, I get 1. Okay, we'll plug in 0, get 1. Plug in 0, get 1. That's fine. We know that cosine values could change signs. It could be positives or negatives, like the cosine of pi is negative 1. Well, here we see these slopes changing signs. We can kind of see how we have this kind of cosine graph created. It's not really that this creates the cosine graph. It's that like they create the sine graph, which is the antiderivative of cosine. You could kind of see that. Versus e to the x, all the slopes have to be positive because no matter what value you plug in, you'll get a positive value. If you plug in like negative 3, I'd have 1 over e cubed. Plug in negative 3, 1 over e cubed is going to be a small value, so a small slope. We can kind of see that here. So that's how we can potentially understand what dy dx creates what thing. We have another question below. This is a good question where it's like, hey, it's a little bit more involved on finding which one is going to work. So why don't we do that, and then we'll talk about what the solutions will look like. Which differential equation creates this slope field? Well, what do we notice? We notice that we got this undefined when x is 0. So that's not that. That's not that. It's either this one or this one. Cool. But which one? This one or that one? I don't know. Let's look at some other ones. We could either go to certain quadrants. We can go plug in like 1, 0, negative 1, 0, see that the slopes are positive. We could see that 1, negative 1 produces a slope of 0, so something along this line. You figure it out. Which one's going to be it? If I plug in 1, 0, my slope should be positive. If I plug in negative 1, 0, my slope should be positive. If I plug in 1, 0, I have a positive slope. 1, 0, I have a positive slope. Okay, so both of those check out with 1, 0. If I plug in negative 1, 0, I should have a positive slope. Well, negative 1, 0 plugged into here gives me 1 plus 0 over negative 1. That's a negative slope. If I plug in negative 1, 0 here, I get negative 1 plus 0 over negative 1. That's a positive slope. I'm thinking this guy. But let's confirm. If I plug in 1, negative 1, I should get a slope of 0. Well, if I plug in 1, negative 1, this would be 2 over 1, which is 2. If I plug in 1, negative 1, that will create a 0 here. So that confirms I got that. You're in charge of and these are tricky multiple choice questions, like here's a slope field. Which of these dy dx's creates the slope field? Essentially, you're doing all 4 of them, but we can go and kind of do a process of elimination where we see some very specific slopes from our slope field, eliminate some of our answer choices, pick the correct answer choice. So that's the first thing you need to know about slope fields is creating them and matching them. The second thing is understanding how slope fields give you a visualization of your solutions. If these are my slopes, this would be a potential graph, a y equals graph, whose slopes match. This is your antiderivative. you can see what your antiderivative shape would be. You could see the equation. Oh, it's got to be some x squared. Oh, yeah. Also, you know the antiderivative of 2x is x squared. All right, that just makes sense. Like either understanding antiderivatives, you could do that. But let's say you didn't know how to take an antiderivative. You could say, okay, x squared fits these slopes. I could find the antiderivative shape. And again, this whole idea of x squared plus c means like I could have any x squared shifted up anywhere. And that would be my antiderivative, my solution, my y equals antiderivative of dy dx. Here, this is what the solution would look like. Something that goes over here. Maybe we're going to go on the other side. We should recall this is what the graph of log x looks like. If you don't recall it, you could just think, just for this one example, oh, 1 over x's antiderivative is log, it should be absolute x plus c. So that like works out, that makes sense. Like the antiderivative of 1 over x is log absolute x. Boom, you can kind of get to that point without taking an antiderivative by seeing it. Here, would be the shape of the solution. Oh, it's got the point 0, 0. Oh, that's like the sine graph. Again, I didn't have to know that the antiderivative of cosine was sine. But I do, and this kind of confirms it. That's like the power of a slope field, visualizations of solutions. Here, if I pass through this point, I can see this is like a cubed graph. Oh yeah, that makes sense. Like x squared's antiderivative is 1/3 x cubed. I know that, but let's say you didn't know that. You'd be like, oh, here's a slope field. This is what fits. That looks like a cubed graph. That would be a solution. The antiderivative of e to the x is e to the x. The graph of e to the x looks like this. This is e to the x shifted down a little bit. That one goes with that one. And then, oops, start with the point. It'll be easier. This graph of this v. Now, this is a good one. This is a perfect one. We don't know what the antiderivative of absolute x over x is. Turns out the antiderivative of absolute x over x is absolute x. Like, again, you didn't know. I didn't know the antiderivative of absolute x over x. Turns out it's going to be the same shape as absolute x. I hope that makes sense. Like, what we are trying to do is like get our antiderivatives without taking our antiderivatives. The green graphs here are the graphs of our antiderivatives. The slope graphs are the graphs of our derivatives. Cool. Now, we're done with the sidebar. Now we are back to taking antiderivatives. When you're asked to find a solution to the differential equation, you're asked to take the antiderivative. It's a funny math way of saying, like, yeah, what's the antiderivative? What's the original equation? Careful, they ask you to put your equation in the form y equals f of x. Guys, this is the key part to this homework. The slope fields are important, sure. A couple questions on your test. Almost all of the questions on your test, like all the rest of your questions are just taking antiderivatives. And these last two lessons are where the big ones come from, where the free response questions come from. Here's what we got to do. Step one, separate our variables. dy dx is not something that has to stay together. it's actually dy of small change in y divided by a small change in x, you can move dx to be on the right side. We will always do this. We'll always multiply both sides by dx to start. Now, I don't want to see you make this mistake, but a lot of students will make it. Move y or y's algebraically so it's on the left side. Sometimes you'll have to multiply. In this case, since I'm dividing by y, to move the y, I'm going to multiply both sides by y, so it goes away on the right side and it remains on the left side. Sometimes you'll have to divide. Make sure you do the right thing. Don't do the same thing every time. It's a huge mistake students make. I'd multiply in this case because I have this y in the denominator, and I get y dy equals x dx. Okay. Now we are set up to take the antiderivative. Now, a big question is what's the antiderivative of y? Well, it's just like the antiderivative of x's with respect to x. The antiderivative of x is 1/2 x squared. Big question always comes up. What happens to dx? Where did the dx go? Well, you just took the antiderivative of x with respect to x. It's gone. I just took the antiderivative of x and it's 1/2 x squared. So it's gone. You've done it. When you take the antiderivative, dx goes away. The antiderivative of y is 1/2 y squared. You only need 1 plus c on one side. 1 plus c on one side. There's my plus c. Put it on the right side because we have to solve for y. Have to find c, but you can find c whenever you want. What we need to pay attention to is how c's may change, but sometimes it's easier to just say, oh, this first c is different than this second c. What do I mean by that? This number for c, if I plugged in 1, 4, I could get my answer for this c. But let's say I multiply everything by 2 because I eventually have to solve for y. You get y squared equals x squared plus, well, 2 times c1 I could say is just a new c, c2. c2 and c1 related to each other, different values. No matter when you find c, we're all going to end up with the same final equation. Let me show you. And again, you could find c whenever you want. You could wait till you solve for y to find c. And this is new because usually you had everything solved for y. 1 is an x, 4 is a y. You could plug in, let's do it here, 1 and 4, giving me 1/2 times 16 equals 1/2 1 plus c1. That's 8 equals 1/2 plus c1. c1 equals 15 halves. Cool. Or if you plugged in 1, 4 here, you'd get 16 equals 1 plus c2. Oh, c2 has to be 15. Oh, c1 and c2, different values, but here's the relationship. You could have either found c1 here, but then as you solve for y, you're going to change it into the correct next c. Or what we're trying to tell you, what I'm trying to help you out with is find c whenever it's easiest to find. Sometimes it's easier after your first step. Sometimes we want to simplify a little bit and find it later. This is especially true for the last lesson, where it's don't find c yet. It's going to be crazy. Wait till we do the little bit of stuff and then, okay, now find c. It's a lot easier. So I think this is an example because it's all right, we just got rid of fractions. Now we just have whole numbers and we just get 15. All right, the last step is to solve for y. Now here's the heads up. When we square root to solve an equation, we need a plus or minus. However, you're not allowed to have a plus or minus because you're supposed to have a function. You were told that when you plug in 1, your output should only be 4. When I plug in 1, I'm having the square root of 16, which is 4, but I'm saying, oh, plus or minus 4. Well, using this initial condition, you know that your y's have to be positive 4. This is how I'm going to say, no, I don't want a plus or minus. I just want the plus. I use the initial condition. I pay attention to the y that I get, and boom, pick that one. We're going to do this one, and we see the y here has to be negative. Well, we're going to get a plus or minus for this one as well. For this one, we're going to pick the negative half, and that produces a function. It essentially just like takes your solution that you can see, and it just like cuts it off so that we're only talking about the correct half of things that we want so that we have a function. Okay? So try the next one by yourself if you haven't tried it yet. It's really the same process because y is in the denominator. You end up with the very same looking solution, just a different c, maybe a different little stuff inside the c. Let's see. I'll do it as well. I'm going to get rid of dx by multiplying it. Always multiply by dx. It'll pop on the other side. Adjust and adapt based on where your y's are. I'm going to multiply both sides by y because y is in the denominator. I want to get rid of it. Don't make a mistake on this first step. Antiderive both sides. When you take the antiderivative, the dy and the dx disappear because you're taking the antiderivative. So I got 1/2 y squared equals negative x squared plus c. Find c whenever you want. Let's say you multiply everything by 2 to get rid of this 1/2 so I don't have to deal with fractions. Well, that's good. Just understand that when you multiply this c by 2, you can write it as 2c, or I could just say this is C2. C2 is equivalent to C1 times 2. I like this form. This is like easy for me to plug in the point 1 for x, 2 for y, giving me positive 4 equals negative 2 plus C2. C2 has to equal 6. If we got C1, C1 would have been 3. C1 would be 3, but then you'll have to multiply by 2. You'll get 6 in your equation before you solve. Now I have y squared equals negative 2x squared plus 6. I want to solve for y. I'm going to square root both sides. I need a plus or minus, but I don't want a plus or minus because I have a function that I want. I have to have one output for every input. I pay attention to the fact that when I plug in x's, I need to get a negative and only a negative y. I only want negative y's, so I'm only going to pick the negative half of things. Okay? This is my solution. We're good. Now, we're going to start to see free response questions on your test. It involves these questions where you're taking antiderivatives and involve lots and lots of steps. There's partial credit given. Separating your variables, taking antiderivatives, finding c at some point, solving for y. 5 points. There's partial credit where you can get 3 out of the 5. You can get 4 out of the 5. So know that just do your best. When we get to free response, just don't put nothing down. Okay, now I got y squareds, but this first one, y squared's in the numerator. Okay, heads up, let's not make a mistake here. Sure, multiply by dx. You'll do that every time. Every single time you'll multiply by dx, so the dx is on the right side. We have dy equals 2xy squared dx. Divide by y squared so that the y's go away. Now, when you divide by y squared, you could write it like that, but I'm probably going to just immediately either write it like this or write it like that. If you divide by y squared, it's the same as multiplying by y to the negative second. I like negative exponents because I can use the power rule to take the antiderivative of negative exponents. So whatever you want to do it, so long as you end up either here or here and are not confused by that. Okay. The right side, make sure the x's stay where they are. If the x's started in the denominator, keep them in the denominator. If the x's start in the numerator, keep them in the numerator. All right. Take the antiderivative of both sides. Away we go. I get y to the negative first times negative 1 equals x squared plus c. I will rewrite this as negative 1 over y equals x squared plus c. We can find c now. Find c now if you want to. This is not a bad spot. I could solve for y and then find c later, or I could find c whatever I want to. I'm going to plug it in now. I got negative 1/4 equals 1 plus c. If I subtract 1, I get this first c is negative 5/4. It's not pretty, but it's correct. I got negative 1 over y equals x squared minus 5/4. Okay, we need to solve for y. First things first, I'm going to get rid of this negative by taking the opposite of both sides. That becomes a negative, that becomes a positive. I need to get y in the numerator. Common thing we do, it's easy to do, is just flip both fractions. Now, a lot of people try to just flip this and this individually. You can't do that. You have to flip the entire side and put it underneath a 1. There's no plus or minus because I'm not square rooting. We're all good. This is fine. However, if this showed up on a multiple choice question, the College Board does not like fractions in the denominator. Be prepared to multiply the top and bottom by 4 to get this version like that. You can't simplify the 4s. This is it. This is acceptable for free response. This is probably your answer that you'd have to find on multiple choice. All right, so I've already gotten rid of the dx. Leave the x's where they are, no matter where they are. Keep them where they are. Don't always move them up. Here, I got to multiply by y squared. Take the antiderivative. Antiderivative of y squared, y cubed times a third. Antiderivative of 2x, x squared. We need a plus c. Is a great instance of don't find c until it's easy to find. If I multiply everything by 3, this is 3x squared. This is 3c1, which I'll call a different c2. It's just a c. Okay. Now, I'm going to have whole numbers. F of 1 equals negative 2. This will be a nice whole number to find versus a fraction, which then gets multiplied by 3 and turned into a whole number. Again, negative 8 equals 3 plus c2. c2 is negative 11. If I found c1, it'd be negative 11 thirds. It just works out. You'll all end up with the same equation in the end. So that is combined to get y cubed equals 3x cubed minus 11. When you cube root, you don't have to worry about a plus or minus. You just cube root both sides, or take both sides to the 1/3 power. Don't worry about plus or minuses unless you're square rooting or fourth rooting. The last two are good. I don't have any x's in the denominator. I kind of wish I did, but we don't. It'll be okay. Next class, we're going to see x's in denominators. I'm going to throw another one in here. Switch. These are just similar to each other. Good practice of lesson 2 stuff. but they're too similar to do. Get rid of the dx. Great. Here I have to divide by y cubed. Now, however you want to get there, you could multiply by 1 over y cubed instead of dividing by y cubed. That's fine. What I would probably end up with is y to the negative third dy equals sine 2x dx. Eventually, I'll get that. Whether it's 1 over y cubed and then I bring it up, dy over y cubed becomes y to the negative third times dy. Just get to this spot. That way you can take an antiderivative. This is going to be very important for next class when we're going to have y to the negative first, and we'll have log absolute as the antiderivative. Y to the negative second times negative a half. How do you take the antiderivative of this? Yo, lesson 2. You take the antiderivative of sine, because you just have x to the first on the inside. The antiderivative of sine is negative cosine. We got Vegas, and we're undoing Vegas's derivative. You got to be able to get this. You get negative 1/2 cosine 2x plus c. Don't forget about this. This is important with like fractions or like compositions in a denominator, how you deal with that. So don't forget about it. Another situation where I'm going to probably get rid of this fraction. I'm going to multiply everything by negative 2. I get y to the negative second, which is 1 over y squared, equals positive cosine 2c plus c1 times 2 is a new cc2. F of 0 equals 3 means 1/9 equals cos of 0 plus c2. Cosine of 0 is 1. I'm going to subtract 9/9. I get negative 8/9 is c2. Okay. Combining those two, we get 1 over y squared equals cosine 2x minus 8/9. Flip both sides. Square root both sides. When I plug in 0, I better get positive 3. Flip both sides. Don't flip 8/9 and turn it into 9/8. Just put it underneath a 1. Square root both sides. Include a plus or minus. Maybe we need to multiply the top and bottom by 9. When I plug in 0, I better get positive y's. That's why I want the positive half of things. That's a good question. I just wanted to do this one because I just want you to see if you end up with something like this. You're still going to divide by y squared, or maybe it's easier to see that you multiply by 1 over y squared. Now, when you do that, what happens is that you got y to the negative second, or 1 over y squared. Here, this turns into a 1 over x squared. I don't know how many times I see students think the x squareds are going to pop up. They got to stay down. They're in a denominator. Keep them in the denominator. That means this is x to the negative second on this side. Take the antiderivative, and maybe what's advantageous is like when you start, just write everything using negative powers if you want to, like or everything as like in the numerator. Maybe not. Just get it right. There's lots of ways to do it. Just get it right. Both sides antiderivatives are the same. F of 1 equals 1. C is 0. I get negative 1 over y equals negative 1 over x. Take the opposite of both sides, flip both sides, y equals x. That's pretty incredible. I feel like it's more complicated than this. But the fact that you have this point 1, 1 means you have to be on this line. If it was anywhere else, it'd be like a multiple of x. But whatever, we're good. Oh, we have more. Great. What if there's no x's and there's just y's? It's the same procedure. Multiply by dx. Multiply or divide by y. I'm going to multiply by y. That means I'm going to end up with a 1/2 y squared. I'm going to have to square root. What's left on the right side is 4 times dx. Now, it could be 1 times dx, and that'd be fine. If like this was a 1, I'd have 1 times dx. That's fine, because you know what the antiderivative of 4 is with respect to x. The antiderivative of 4 with respect to x is 4x plus c. Antiderivative of y, 1/2 y squared. I'm going to multiply everything by 2. This becomes a c2, c1 times 2. I got the 0.24. 16 equals 16 plus c2. I got another c, that's 0. That's fine. Y squared equals 8x plus 0. Y equals plus or minus root 8x. Well, if I plug in 2, I better get positive y's. I just want the positive. Same thing here. And then we're going to see what a free response question looks like that you're going to have on your test. An example of it. I got dy equals 3y squared dx. I'm going to leave the 3. Don't touch the 3. The 3 is fine. I'm going to divide by y squared. When I divide by y squared, dy over y squared can be written as y to the negative second dy, 3y squared dx. We're good. Antiderive both sides. Let's see what happens. That's just a 3. Y to the negative second equals 3. The y's are gone. The 3 remains. Don't move the 3. If you do move the 3, you could still get the right answer. You'll end up getting the right answer if you do all the right steps. Just the 3 would end up in the denominator here. And then when you move the y's up, you'll have this y to the negative second over 3 or 1/3 y to the negative second. It'll still work out, but just move the y's. Don't move anything else, okay? Antiderive. The antiderivative of just 3 is 3x. Maybe rewrite. We haven't changed c yet. This is still c1. F of 0 is negative 2. I don't see a problem plugging in now. C has to equal 1/2. That gives me negative 1 over y equals 3x plus 1/2. Take the opposite of both sides. Flip both sides, putting the entire right side of the equation underneath a 1. This is fine for free response. For multiple choice, be prepared to multiply the top and bottom by the fraction that you want to get rid of, the denominator. You can multiply the top and bottom by 2 or even negative 2, giving me y equals negative 2. This is positive 6x plus 1. That's good, or that's good. Multiple choice, free response. Oh, that's gross. Sorry. Welcome, my friends, to the land of free response. We've made it. These are probably the easiest free response questions we're going to see for the rest of the year, because it's just like taking antiderivatives. Next unit, which is the most important unit of the entire year, it teaches you calculus, all of calculus. Next unit will be like real world driven. Next unit, we start on motion and we start to applying calculus to the real world. This unit, simple, it's just like take antiderivatives. But here's like how we can split up what essentially is an antiderivative question into multiple parts. For example, here is a differential equation. Okay, it's just a derivative. Pay attention to part A, part B, part C. Part C is find the particular solution. Part C is the part where we want to take the antiderivative. We don't want to take the antiderivative before part C. It has nothing to do with it. There are other questions. Usually with these free response questions, either like part C, like the last part or the second to last part actually has you take the antiderivative. Just pay attention to the directions. Sometimes it would be different. Part A doesn't have to do with antiderivatives. It's like, hey, here's a slope field. Sketch the solution curve that passes through the point 0,2. Well, if I have this point 0,2, it looks like my line wants to take me this way. Looks like y equals 2 solves it. Okay. What about the point 1,0? Well, if I'm going through the point 1,0, it looks like my slopes want to take me this way. And it looks like they want me to go this way. Something like that. Boom, we just got part A right. We got like 1 point. All free response questions are worth 9 points. 1 point, or maybe 2 points, 2 points, 5 points. Usually the big antiderivative step is worth like upwards of 5 or 6 points. Part B, let y equals f of x be the particular solution to the given differential equation with the initial condition 1, 0. Nothing yet. Nothing's happened yet. It doesn't say to find the particular solution. It says, hey, this is a particular solution. Write an equation for the line tangent to this at x equals 1. Use your equation to approximate f of 0.7. Guys, this is a unit 4 question. Tangent line approximations. Tangent line. Y minus y1 equals an m times x minus x1. Remember from unit 4 when we did tangent line approximations, like the line approximates the curve. Points on the line will approximate points on the curve. Y's of the line will approximate a y on the curve. Okay, we got x equals 1. We have this point 1, 0. So I got y minus 0 equals some m, x minus 1. What the heck is m? Well, here's where a lot of people will have difficulty. They think m must be this entire equation, and they put this entire equation in for m. No. However, this equation, and again, you got to look back, this equation is your slope generator. It generated this slope here at 1, 0. What is that slope? Well, plug in 1, 0 into this dy dx. I got 1/3 times 1 times -2 squared. I get 4/3. 4/3 is my slope. You're going to see this on your test where you're going to use a unit 4. It's a unit 4 question as a part of this overarching big free response question. We're going to use it to approximate f of 0.7. Guess what? This is an acceptable answer. This is what's called an unsimplified answer. That's okay on free response. Thankfully, on the AP Calculus test, they don't worry about simplifying. The pre-calculus test, they do. On the calculus test, this is sufficient. What we don't want you to do is simplify incorrectly. If you're going to simplify it, do it correctly. This is -3.3. This is -3/10. And you can write this as -12/30. Oh, divide the top and bottom by 2. And it's, wait, the 3 cancels. It's negative 2/5. 4/3, negative 3/10. Yeah, like that's great. If you get that, great. This is fine. Okay. And if you're listening to this video, remember this. And I know you're going to be weirded out. Like, what do you mean? I could just leave this? Yes. Now, let's do the good stuff. I wish I had more of these in the homework, but let's see. Solve. All right. Separate my variables is going to be worth 1 point. Going to multiply by dx. I get dy equals 1/3 x y minus 2 squared dx. I need to divide by my y's, but my y's are inside this square. Guess what you're going to do? Divide by y minus 2 squared. Now watch what will happen. I rewrite this as y minus 2 to the negative second. Because I can take this antiderivative. Now, this is like a Vegas deal. What starts in the parentheses stays in the parentheses. Make sure you undo the derivative of the inside. The derivative of the inside is just 1. I don't have to worry about undoing it. So all I have to do is take the antiderivative of the outside and then Vegas. Here, unfortunately, we got a bigger fraction. And get this. Now's a good time to find C, to be honest. I don't want to find it later because it doesn't look like it's going to get any easier. Maybe I could take the opposite of everything, and this would become a C2 after I take the opposite of C1. But I do have the 0.10. So using the 0.10, I will plug in 0 for y, 1 for x, that's great. I'm going to add a 6 to a half. A half is negative 3/6. And this is where, like, you got to be okay with answers that look messy. It's free response. Just get it right. Adding a 6, I get negative 2/6, which is negative 1/3. If you leave it as 2/6, it's fine. You're 4 of the 5 points on the way. The only thing you have to do is flip both sides and add 2. Watch how that looks. And watch how you have to be okay with something that looks this gross. That's correct. I flipped this side, and then I added 2 to the end after. I didn't try to incorporate it into my fraction. I didn't try to use a common denominator or anything. You could, but it's free response. If I'm going to tell you anything about free response, it's like ugly answers that are unsimplified are okay and will be accepted. Okay? Let's keep that in mind for this one. Okay, write an equation for the line tangent to whatever my solution is at x equals 1. Well, I have the 0.12. I have a slope generator. So I have y minus 2 equals, what is dy dx at 1, 2. That's how I'll get my slope. 8. Boom, 1 point. Yo, more uniform. Use the tangent line equation to approximate f of 1.1. Given that y is positive for x's between 1 and 1.1, is your approximation greater than or less than f of 1.1? This is the idea that you need to remember that lines on curves can be under or over the curve depending on the curve's concavity. What determines a curve's concavity? The second derivative. It's starting to build upon itself. The stuff we learned in the first semester is not going away, especially for the first lesson of Unit 7. You'll see. It's like everything we learned in the first lesson of Unit 7. Everything we learned in the first semester shows up on the first lesson of Unit 7. So, f of 1.1 is approximately whatever this y value is when I plug in 1.1. That's 8 times 1.1 minus 1 plus 2. Do I need to figure out what that is? No. You could leave your answer like this. It ends up being 2.8. If you get that, hooray. Is this over or under? Well, my second derivative has positive y's for x's that are positive. If I plug in a positive y and positive x's, my second derivative is positive. That means y equals f of x is concave up, tangent line, values on my line, the y values on my line are under the y values of my curve. This is an under approximation. So 2.8 is less than the actual value of f of 1.1. Review. Part C. Find the particular solution. Oh, they're finally asking me to take the antiderivative. All right. Multiply by dx. Divide by y cubed. Or multiply by 1 over y cubed. When I divide by y cubed, I might as well write it as y to the negative third. So I can take the antiderivative using the power rule. Y to the negative second times negative a half. 1/2 y cubed, or 1/2 x cubed, plus a c. I'm going to multiply everything by negative 2, get rid of at least some fractions, turning c1 into c2. That's nice. I have a 1/2 on both sides. I have the 0.12. C2, therefore, is 5/4 after I add 1 to both sides. Okay, get ready. Flip both sides, square root both sides, but we only want the positive half of things. Because when I plug in 1, I need to get positive 2. Flip both sides. Completely flip it. If you want to multiply everything by 4, go. Square root both sides. Think about the plus or minus that will show up. But when I plug in 1, I better only get positive 2. I mean, you could also check. If I plug in 1, I get negative 1 plus 5/4. That's 1/4. 1 over 1/4 is 4. Square root of 4 is 2. I want the positive 2. It works out. It checks out. Free response question, 9 points. Your test is 50% multiple choice, 50% free response. All right. We'll see you out there. Next lesson is more of the same, but more difficult. Later.